All right. So the same idea. We just did something where we had to do this kind of crazy, weird little calculus thing where we added up everything, and then we had to. The question asked us to break it into components, so we just had to use sine and cosine. Do you remember this? Is this seem familiar? Yes. Right. We had the one. It was white is not a good choice. So it was like this at some point here. So we did a little tiny thing here and got E from that, right? And then we added up all of those along this length, and then that gave us some net E. And then we just had to take that net E and then multiply it by cosine theta and sine theta, which we extrapolated from this, right? Cosine being whatever this was, x over the square root of whatever y squared plus x squared, and then sine being y over that. So we just took those terms, the cosine and the x, and multiplied by that. Now, this one has the fun little capacity of giving us this advantage that all of the charges are the same distance away from the point of interest. We just have to make sure that we're dealing with kind of the fact that the angle will change things. Okay, so then in that respect, that's why we're again saying that this is going to have two parts, EX and EY, right? And then our basic statement is that E is delta Q, once again, our sort of little small charge. What is the effect of that little small charge? It's the delta Q over R squared, right? Of course, 1 over 4 pi, whatever. The R doesn't change, so that's why we go to the capital R. Right? That capital R is because R is constant. Then you'll remember me talking about this. I hope you do. This lambda, which is the linear charge. Okay, that's linear charge density, right? You'll remember I presented two possibilities. You can either say that delta Q. You can say something like delta Q is going to be the linear charge density times whatever, I don't know, delta S or something. Yeah, because it's an arc, so we're taking some little tiny piece of that arc. You can also say, alternately say, delta Q over delta S is proportional to like the total charge over the whatever the total arc length, which it's a quarter. That'd be, what is that, pi? Half would be pi. Is that pi over 2? Yeah, it should be pi over 2. Okay, that looks like tau times r, right? So, do you see what I did there? Just took the length of that, the charge divided by the length. So remember, you can do that either way, and that works when you're doing moments of inertia. It works here. You can use the ratio or you can use the density. It's the same thing, but whatever. However you like to look at it. Anyways, that's how they get this, right? They do Q over L, and then L is pi over 2 times R, so the 2 goes up there, and we get this part. Where we get the delta Q. Then we can substitute that in, and once again, we just go with the sine and cosine terms, right? And then you can see here, oh gosh, where's that? Yeah, just some, I don't know, algebra stuff in here, like they put delta Q over R squared, then this is the substitution in here, and then that gives us this second term here, right, with the 2Q. And then ultimately bringing that out, just doing a little bit of algebra. Okay, so this is going to give us our two components, and then for B, so for part A, write the expressions for the x and y components, so we're good there. For part B, write but do not evaluate definite integrals for each, and then evaluate the integrals. So here we're taking our the statements for the two components, and this would be like the sum of these things, right? But we're saying that E is going to equal the E for each little charge unit is that. I'm surprised they didn't. Oh, okay. I guess they're saying these are the components of that original delta Q charge. If you were going to try to write these as complete statements, you would say the sum of these from 0 to pi over 2. And then that, of course, the next step there is to go into our integrals, our integration. Notice, same thing, right? All we've done is pretended like there was a sum on here from 0 to pi over 2. Right? Is that reasonable? Everybody kind of okay with that? That's all that is. Just have our little sum statements and then turn those into our integrals there. We haven't done anything yet. The integrals are very easy because it's just the integral of cosine and sine. All right, questions? Yeah.
Yeah, I'll put all that algebraic
Gobbledygook here.
The first expression, I don't see how that relates to the second expression.
This one right here?
This one, and then the next one.
And then this one, or this one and down?
Right.
Okay, all right. So does this part make sense to you? Actually, you know what? Let me do this. Make this a little bigger. Okay. I don't know if that's more visible or not, but wait. Does this part make sense to you? Right? This is just E of x is k delta q over r squared cosine theta, right? And that's just the k. Okay. Now what we did up here is we said delta q is equal to the charge density times the slight delta arc length. Yeah. Okay. So from that we said what is charge density? It's q over L. And what is L? It's pi over 2 times r. Right? Does that make sense? Yeah. Okay. So then that gives us this term. So now we can just take that term and stick it right there. Because now, do you see like here, if I get rid of that k, this right here is this. I've just taken out everything as constant. Because r is a given distance. Since we're on the circle, right, every point on our line of charge is the same distance from the point of interest. So our r is a constant. So I can just move it to the outside, and then our delta q becomes 2q over pi r, right? And then our delta s, what is delta s? Well, what is s? Right? That's just, right, r theta. That's basically what they do.
Right.
Does that make sense? And so then from that, and yeah, once we plug that in, this r cancels with that r, and then we can deal with the charge is given, so that goes outside, and I'm just left with cosine theta delta theta. And then that lets me, that's my sum statement from 0 pi over 2, so that lets me go right into my integral. Yeah.
Why do you have to count that R? Can you, what was the delta Q of the...
Oh, like all the way over here?
Yeah, the dot in the middle. Like how
Dot in the middle.
Like what is delta Q?
Oh, okay. So, yeah, I hope you don't mind if I keep. I'm trying to connect both the moment of inertia concept with this because the math is exactly the same. So remember when we did moment of inertia, we said we want to take some really thin slice of this mass and say that mass has an effect on the moment of inertia around this pivot. Okay, so we did delta m, and then we said delta m is actually the density of this object, whether that's mass over length or mass over area, whatever, that's times the delta r, right? So here, so we took the basic statement, which says I is mr squared, and we took a delta m and then changed it into delta r. So here, what we're trying to do is we're trying to get a piece of charge, and we're saying, what is the effect of this little piece of charge at this point? And we know that the effect of a charge at a given radius is k q over r squared.
So it's the charge of the
Yeah,
circle.
so first we're taking the 1, and then we do it across all of them. Right? So same thing. We say that little delta q, we need it in terms of this length. Right? And that's how we say, but wait a minute, all of the radii are the same, yes, but how do we sweep across a quarter circle? Well, we do it by changing delta theta. And so we want to get the theta eventually, so we can add up the effect across all of them.
So you can't just assume that it's like a whole circle and then you go from there.
Well, the whole circle, let's think about that. Nah, because then, okay, what would be, this is a good point, what would be the electric field in this situation? Is this AP? If I do this nice and evenly. Okay, so let's say, so you have this ring, okay? Now that ring has a charge. It has a charge, okay, it has a charge Q, and it has a radius capital R. What is the electric field at the center? Discuss. Go.